hope my voice is clear. So I will start with yeah. We will have before that we will have brief introduction of what exactly we have learned so far. So let's begin session 4. Yeah. So in last session we have seen so in last session we have discussed many things. So first with interfacial energy or surface energy mostly. So and yeah, I have told many times, so surface energy comes from the the formation of new surface, right? And the energy term comes from when you form a new surface, you break the bonds, right? So when you break the bonds, you have extra energy, and that energy you call it as a surface energy because that energy needs to be supplied, so by any means, such that we can create a fresh surface, right? So that's what surface energy terms come from. And then we have discussed few things about how the surface energy depends upon the number of atoms on the surface. So after that we have discussed Wolf diagram or equilibrium shape diagram, how it forms. I will again discuss this because Sarah has discussed the same thing again, so in brief manner. So we'll do that again. And yeah, after that we have discussed some curvature part, and because of the time limitation we have ended that curvature thing, right? So yeah, I will just start with that curvature part, right? So yeah, in this session we will discuss again the diagram, right? And then we will discuss some part of so this is very important, right? Because whenever you are study for grade exams also, this thing will always come, right? So there is this term called the surface energy. Surface energy of an atomic plane. Yeah, this thing will always come. Whether you talk about FCC, you will talk about BCC. So they will stick with FCC and BCC because when you go to higher crystal structures, like HCP, or they will become more complex, right? So when you're talking about triclinic monoclinic, they will not do it normally because it is more complex than other things. So yeah, and then we will discuss thermodynamics part. See, Sir has proved, but there are few things that he has missed to explain. So I'll do that in this session, right? So yeah, and beginning with the curvature part. See, this thing we have seen it, right? So this is the TM image. You can call it as a HRT image. Called as high resolution transmission electron microscope, right? So this is a high resolution image. So you can see these are the lines, right? You can see the lines. So these are the set of atomic planes. And this is one nanoparticle and this is another nanoparticle, right? Now what is happening is when they are close to each other, there is this formation of a neck region, right? You can see this neck region. And how it is formed? Because of, yeah, just like I've said before, when there is a surface energy, the energy is, the surface atoms are have higher energy when compared to bulk atoms. So they need to decrease the total energy of the system, right? I have explained before how the nanoparticles have high energy when compared to the bulk particles, right? Because most of the atoms are lying on the surface, and because of the total energy of the system is higher. So to reduce the total energy of the system will try to bond with other particles, right? So that the total energy will get reduced, at least some part. So to reduce that, there is a need for the diffusion, and diffusion happens, I guess everyone knows the Fick's law. So Fick's law states that the diffusion will depend upon, or the diffusion flux will depend upon the diffusivity times the concentration gradient. The flux is given by, or you can call it as, the concentration gradient. Right. Now what is this concentration gradient tells us? Right. So concentration gradient means somewhere you should have high concentration and somewhere you should have low concentration. Then only this moving from high concentration to low concentration happens. It's just like the flow of water. So you need, if you want to flow a water from one place to another place, then that water should have high potential energy or high kinetic energy to flow it, right? So for example, see, what I'm trying to do is I just put a ball here on a surface and it will not move. What happens if I remove this surface and the surface is below? It will fall down. Why? Because it has a higher potential energy. So the same goes here. Now there is a need for concentration gradient. And who is giving that concentration gradient, right? So dC by dx. So who is delivering this? This is delivered by atomic diffusion. Right. Now how this, see? So whenever you have a particle and they come close to each other, so the necking will increase. This is at time t equals to 0. This is at time t equals to t1. So what is happening? Some part of atoms are moving from here to here. Then only this neck region will increase. Right? At first there was a very little thin region, and now let's say it is x1, and now it is x2. And we know x2 is greater than x1 in thickness. And how it happens? Because of the diffusion of atoms. Now how the diffusion of atoms takes place? Because see, here you have the same surface atoms, here also you have same surface atoms. Now for the surface of atoms, for example, let's not even talk about the surface of atoms, right? So let's talk about how the diffusion of atoms takes place. So for atoms to diffuse, or the atoms to move, there needs to be a gap, right? So there needs to be a gap in front of them. Then only they can take that place. See, I will show you. So for this atom to move, they need a gap. It needs a gap, right? So it needs some space, and that space we call it as vacancies. So for atoms to move, there needs to be a vacancy gradient. Now again, so for atoms to move, you need vacancies. Now the question is, how do you create, again, so how do you relate them? So if this is my atom's diffusion, atom's flux, which is equal to minus of flux of vacancies. So if the atoms are moving this way, then vacancies move with this way. So that's why I put a negative sign here. It's the opposite motion, right? So if our atoms want to move here, then the vacancies will move the counterwise. Now, so this is so far the relation we have. Now again, where do we find the vacancies? So, and here the relation helps you. And last class I have also explained how do you take the curvature, right? For this is our convex, and if you have concave, who should have a positive curvature, who should have a negative curvature, right? I have explained in terms of Taylor series. I hope you people remember. right? So it was more or less the average values around f of x minus f of x naught, right? If this is positive, you will have a positive curvature, and when you will have a positive curvature, when the average values are at higher values when compared to the ground value we are comparing, then we call it as a positive curvature. And what about for the convex? The convex, the value we are trying, the average values are at lower levels when compared to the value we are going to take, right? So the never values are at lower level, then this will become negative. So that's why the convex has a negative curvature, right? And there is also another relation. How do we give it as a kappa? Kappa will be equals to, there will be a constant c by r, okay? And this c by r depends upon the geometry, right? If you take a sphere, it will be 2 by r. If you take a cylinder, there will be some other constant. If you take a cube, then it will be 3 by r. So like this value changes. It's not just 1 by r, okay? So the curvature is proportional to 1 by r, but when you remove the proportionality, there will be a proportionality constant, and that is k, okay? So that is c, right? So generally we take it as 1 by r when we are talking about the normal curvatures, the 2D curvatures. When we are talking about 3D curvatures, that thing will change, but again, that is not related to this course. So let's move on. Yeah, where will be the vacancies, right? Now, this is the relation we have derived. I hope I don't need to derive again because we have derived it many times. 2 times, I guess. One sir has derived once, and I have also derived once. So, yeah. And we know this is our convex and this is our concave, right? So convex atoms are moving from here to here. Then that means the concave, this region has more vacancies than this region. So vacancies are moving from here to here. That's how you do. You find this cold sintering type in the nanoparticles. Right. So that's the theory behind it. Okay. Now let me check the questions actually, so that I can give example here, right? So with the theory I will also explain questions. So just a second, I have note today. Yeah, so we need to discuss about, yeah, there is some part of thermodynamics also, right? So okay, then we'll do that. And then instead of that, let's move on to the surface properties. Now, I hope I don't need to derive this relation because sir has derived very like in detailed way. So he didn't miss any parts, so that there is no need to go again there. If you have any doubts, I can explain again. So yeah. Now, yeah, so the lattice parameter changes. Now, how the lattice parameter changes? Because see, this is our actual relation. If you see, right? So this is actual relation. So when the particle size decreases, right, our lattice parameter will change. See, and it will go down. Right? So because this goes down, this goes down, and this will go up. So that is a relation, right? There is a need for change. Now, yeah, I hope I don't need to explain this again. Then moving on to here. So there is a term called, in nanomaterials we talk about the magic numbers. Right, so what do I mean by magic numbers? So, see, there is if people have studied physical metallurgy or any type of courses which involves the crystal structure formation, how you will have crystal planes or any crystal structure or any material nucleate, right? So whenever you have a Okay, in more layman terms, so for example, if you have a liquid and if you want to solidify it, okay, so for example, you have water. Now what you are trying to do is you are trying to cool. So when you try to cool, the icing doesn't happen abruptly, right? It just doesn't happen throughout the medium in milliseconds. It starts to slowly. It starts at the corners or at the walls, and then the ice will slowly come towards the center during solidification. So the solidification happens in alloys and steels in the same way. So to nucleate, the atoms must come close together. So then only we will differentiate from fluids to solids. So what is the main difference between the fluids and solids? The density. Then the density of atoms. And the other thing is the flowability. Right, this is flowability is more related to the mechanical one. See, that's how they differentiate liquids and solids. But we metallurgists, they like differentiate liquids and solids depending upon one is the crystallinity and other is the density of atoms. Right? So yeah. So whenever a liquid becomes dense, it will become solid. Right? And there is other thing also, supercritical fluids. Let's not discuss about that because it is if sir discuss more about thermodynamics, then I will explain that. So if not, then let's leave it because if you study in deep the thermodynamics part, then you will come ahead of the term superfluids, supercritical fluids, where the density is so similar for fluids and solids that they are immiscible. You cannot differentiate between fluids and solids. Right? Okay, let's leave that for time. Now, whenever you have a nucleation, right, you have atomic planes. Stacking on each other, right? So for FCC, you will have ABC type. So for example, so these three atoms, right, are below me, then the other atom will come above it to cover the voids. Now, so the same goes, so this is how they look like, right? So 3, and then you will have 6, 1, 2, 3, 4, 6, yeah. And then again you will have 3. So that's why we call it as A, B, C. So this again you will repeat. On C you will get an A, again on IA you will get B, and again on B you will get C. So that's why we call it as ABC sequence. Now when you see this one atom, right, this one guy, first it is surrounded by 6 atoms, right, and then on it you will have 3 atoms, and again below you will have again 3 atoms. So these 13 atoms will first come together. So that's why you got 30. Again, after that, again some atoms will come close together, you will get 15. Again you will get some atoms close together, you will get 147. So these number will not change for FCC. If you are talking about FCC, this number will not change. These number of atoms will come close together. Now again, why? To reduce surface energy. You can see how the surface energy is decreasing. Right? So again, decreasing corners and decreasing edges will also implicate your surface energy. Right? So that's all. Now, yeah. So this was the relation. Again, I will just give it a small recap. Okay. So let's say this is a simple cubic unit cell. Simple cubic structure. Okay. Just give me a second. Let me check. Yeah. Using particle size lattice parameter of nano. Okay, so I have seen these questions. Okay, so again, so there is term called isotropic and anisotropy, right? So I hope you people have listened that. So isotropy, before going to this, isotropy, and there is another term called anisotropy. See, here you can see whenever you have this sphere, okay, the sphere type structure. Now, if you have a sphere, then wherever you point it, you will have a radial direction, and that will not change. Right, so that's why you call it as isotropic. And when you go for other dimensions like cylinders, cubes, for example, the isotropic, the nature will not be the same, because when you, the distance between the center, for example, if you take a cube, right? So the number of atoms, right, arrangement will be changing from one direction to another. In FCC, so 100 have some set of lengths, some set of atoms. 110 will have some set of atoms. 111 will have another set of atoms. Okay, we will come to that slowly. So at first you have isotropy. Okay, this is the change. Isotropy is nothing but in whichever direction you go, the properties will not change. And anisotropy is nothing but, so whenever you change the direction, your property will change. Right. So that's the difference between isotropy and anisotropy. Okay. Now let's come to Wolff construction, because this is very important, which defines this structure. Why it should have this many faces, why it should have this many faces. So it will decide which structure will get how many faces. Right. So the Wolff construction will come from simple construction or simple cubic structure. So again, simple cubic structure is nothing but, I will write, let's write a black. Okay, so you have 8 corner atoms, right? Let's change this color to orange. It is more visible. Let's change it to blue. Okay. So you have like 8 atoms at the corners. Now what is the effective number of atoms? See, whenever you see here, see each cube, so for example, this is a sphere. Now on the left you will get another lattice, on top you will get another lattice, on bottom you will get another lattice. So this is in one plane, okay? So let's say this is a plane we are talking about. Now whatever the above one or the out of the screen, see you will have another lattice here, right, in front of the lattice. So this will be my y-axis, this is my x-axis, or this will be my z-axis. So before you will get another one, and cross diagonally you will get another one. So this guy, there are three, and then top the same three. So each cube is shared by how many? 4 and above 4. So 8 unit cells. So each corner, that means each atom at the corner. So each atom at the corner is shared by 8 unit cells. So the contribution for this unit cell will be 1 by 8. Now how many atoms are there? 8. So effective number of atoms will be 8 cross 1 by 8 equals to 1. So for simple cubic, the effective atom is 1. So one crystal will contain, or one unit cell will effectively contain 1 atom. Okay? Thermodynamics, it's way too soon. Yeah. Coming to this guy. Now I will draw the simple cubic unit cell again. Okay, you have an atom, all the corners. Now, so what I'm trying to do is, I'm trying to first cut here. Cut this cube in half. Right. So each atom will lose one bond. Right. So you can see here each atom is coordinated with here, here, and here. Right. That means it is coordinated with the coordination number. Right? So the coordination is 4. So the coordination number is 8. Coordination number, yeah. It is lost by one bond. So whenever you try to cut the surface, one atomic bond is lost. Now what happens if I try to, so these are the unit cells, right? So each one is a simple cubic unit cell. Now what I'm trying to do is, I'm not trying to cut it perfectly in half. I'm trying to slash it along some direction. Right. Now this direction makes an angle theta with the x-axis. So let's say the slash is unit length. That means 1 centimeter or 1 mm. Right. So we know again each bond length is A. That is nothing but the lattice parameter. Okay. So yeah. Now again along x-axis, we know the x-axis length is, and because this is 1, so let me draw the triangle here. If this is 1, then what is this guy? And what is the length of this guy? Right. This length will be sine theta, because the length is 1. It doesn't, because it will not change anything. And this length become cos theta. So along x-axis, the number of bonds are being broken will be cos theta by A. Now YA, because the number of bonds, right? So for example, each bond length is A. Then if you have a 1 unit, then number of bonds will be given by, so A. So you just divide it by A. Right, then you will get this one. Right. Now same for z-axis again, if you have a unit length, then the number of atoms being broken will be 1 by A. And the same for y-axis will be A cross 1 by A. is the number of bonds being broken. This for along z-axis. So we are taking the area type, right? So that's fine. Now this will become cross, or you can call it. We can take it as bond energy, right? So each bond breaking energy. Okay. Now this will become 1 by a square. If you take common, it will be a square, and then you have cos theta plus sin theta, and it will be half, because each atom, each bond will get the bond breaking energy divided by 2, right? So if you are talking about one atom or one bond, and if I just separate this 2, it can be written as 1 by root 2 a square. So let's take it as separate as. Then it will be 1 by 2 a square, sorry, 1 by root 2 times this guy, and the 1 by root 2 comes here, cos theta plus sin theta. So we know 1 by root 2 will be cos 45 cos theta plus sin 45 sin theta. So this relation looks very similar, right? So it is more or less equals to, it is exactly equals to, not more or less, okay? So cos pi by 4, right? So pi is 180, so 2 times 90, another 2 will be 45, yes, pi by 4. See, I have put it mod because for positive values of theta, you will get the graph like this. Okay. It should look more or less looks like this. You can substitute in values and see for yourself. Okay. So now we no longer have the x and y axis. It's the axis of r comma theta. Okay. So it's a spherical axis with phi being not present. Okay, so it's an r theta axis. So from center to the curve will give a surface energy or the energy, right? Again, for the next quadrant, it will look like this. You can just try to draw yourself and you will end up with this type of curve. A plumb symbol of Wasset. Okay? This is how it looks like. Now, so again, I have explained before, for equilibrium, what should be the minimum value? The energy should be, or the energy, or the total energy of the system. The total energy of the system should be minimum. Now, if this is my surface energy, if every point on my graph gives me surface energy of my system, then where do I find my minimum energy? So I find my minimum energy at these cusps, right? So cusp 1, cusp 2, 3, cusp 4. So these are the 4 points where I find my system to have minimum energy or minimum surface energy. And apart from anywhere else. See, you can find the maximum here, maximum. Anywhere you find, you'll have the maximum, more energy when compared to these terms. So then what we try to do was, so we try to draw a tangent at wherever this our curve touches the point. So it touches my curve here, so I will draw a tangent here. So again I will take another point, my arrow to here, so again I will have another tangent here. Right, I can draw whole number of tangents, but what about if I try to draw at one? Let me draw at one, and then two, let me draw it at two. The same goes for three, the same goes for four. Now if you try to draw the tangents at every part, right, so you just try to draw it. It will be a bit messy, but you will understand, right? So you just try to draw it at every point, right? And you try to draw a fixed length of tangents, and they will envelop like this. They will leave this area, and everywhere you will find tangents. So the equilibrium diagram or the equilibrium shape of a system can be constructed from this Wolf diagram. So the equilibrium shape is nothing but the space enveloped inside these tangents, and that space is this one. Okay, so my final surface will look like, my equilibrium shape will look like this. That's it. So that's what the Wolf construction says. So whenever you try to draw the surface energy in terms of theta or the angle, then you try to draw tangents to your curve at every point, and these tangents will envelop some space, and that space is your the equilibrium shape of your system. Okay, so this is how the Wolf construction comes. And the same goes for these guys. This is for more complex atoms. As I have said before, see, we will discuss that, why the shape changes, right? It depends upon atomic planes. Okay, so how these atomic planes will change our system. Coming to that, we will come to that. So because of those different atomic planes, there will be a complex shape. Okay, so people call it as cubo-octahedron, cubo-octahedron, right? Because you will have 6 faces, and then you have the triangles also. Not only 6 faces, you will have square faces, and you will also have a triangle faces. And I do not exactly recall the number, but that's how it looks like. So because of the atomic planes. Now we know, what if I try to cut a simple cubic cell in any direction, you will lose one bond. Right? Now what if I try to cut an FCC? Then what will happen? So what will be the number of bonds for example, I guess I have explained this before. How do you mention the atomic planes, right? So just I will do a brief recap. Okay. For 100, I will use blue, right? Then my 100 is this plane. So this is my, so for example, this is my y-axis, this is my z-axis, and this is my x-axis. Okay, so x, y, z. Now my 100 plane is this guy. How do you define it? because this plane is neither touching y, it's neither touching z, it's only touching my x-axis. So that's why it is touching at 1. So let's say these points are 1, 0, 0, 0, and this point is 0, 1, 0, and this point is my 0, 0, 1. Right? That's how we represent coordinate axis in 3 dimensions. Right? So it is x comma y comma z. And because it is not touching any other axis, so we just take x as 1, 0, 0. Now, moving on to, let me draw again. Let me represent x, y, x, z. This is 1, 1, 0 plane. Now, so again, any guesses? So first will be, it should cut x-axis here and it should cut y-axis here. Right? Same. It should cut x and y-axis. So first, let's say it cuts x and y-axis. So this is my line because it cuts both x and y. Now it should be a plane. Right, and it shouldn't touch z, so it should be a parallel one. Right. So this is my 100 plane. So 110 or 101, anything depends on where you are cutting the axis, right? And the final one will be. First, let me draw the cube. So this should get an yellow, right? So this is my y, this is my x. Okay. Now my 1, 1, 1. So it should touch z here, x here, and y. It should be a plane, it cannot be a line. So first let's join x and y, and then join these two guys, and then we will join these two guys. So this is how the plane looks like. So this is my 1, 1, 1 plane. So I hope you people who didn't understand or didn't study the physical metallurgy course, so I hope the planes are clear now. Now let's move on to how the surface energy changes with the crystal structure, and also the atomic plane. In last class, I have explained what is the surface energy of an atomic plane, right? So how do you view a surface energy? Surface energy is given by, first, the bond breaking, the energy required to break one bond, right? So one bond divided by 2, because each atom will get half, and then times the number of atoms. Number of, you can write as number of broken bonds. Okay. Now, what do you mean by heat of? Enthalpy of fusion. Enthalpy of fusion is nothing but conversion from solid to liquid. So what is happening here is you are trying to break every bond inside the solid such that it becomes loosely bonded and then they become liquid, right? So in liquid, atoms are continuously moving from one point to another point. That means the the bonds are being totally broken. So that is what the enthalpy of fusion, right? So the energy required to melt a solid. So that is called as enthalpy of fusion. That is given as delta HF, and that will be equals to the number of bonds being broken, and that depends upon coordination number, that is given by Z times the number of atoms, and that is given by Avogadro number, and this is for 1 mole. If you are talking about Avogadro number, then that is for the 1 mole of energy, sorry, not 1 mole, so per mole, the energy required to completely convert solid to liquid per mole. Okay, so per mole of ice, if you try to completely convert the solid to liquid per mole, then this is the amount of energy you should give, so that the entire solid can be converted into liquid, or the heat energy you should supply. Okay, now times, oh sorry, there is another term, right? Sorry, so let me, I missed one part. Okay, so the same, everything goes same. Delta H fusion will be equals to number of Avogadro number times the coordination number. Coordination number is nothing but how many bonds each atom is forming, okay, times the bond energy of each bond. That's it, right? Or you can take it as divided by 2, because if you are talking about each atom, then that is divided by 2. Now, what is this? Delta H 1 divided by 2 will be equals to delta HF divided by N naught Z. See, you cannot find exactly what is the amount of energy, bond energy to break one bond, but you can find delta fusion. That is simple, right? So that this is easily available when compared to this guy. So that's why we are trying to substitute this guy instead of this. So that's why this whole thing I explained. So it will be delta H fusion upon N naught times Z times number of broken bonds. That's it. Now, how do you find the number of broken bonds? So this is surface energy for, let's talk about FCC. Okay, the surface energy that required to break bonds for FCC. Let's start with that. Right. Now, let's start with easiest one, 100. I will derive it for 100, 110, 111. You can try it for higher order atomic planes. Okay. So let's start with 100. Now, see, you need to clearly visualize the structure. Otherwise, you cannot exactly tell. Okay. So this many atoms are broken. So I will try to write the structure as much as possible, so that you people can understand or visualize. Okay. So let me draw big structure. Okay. And we know how the FCC looks like, so I will not explain it again because I have already explained it. So let's take, so 100 is nothing but this atomic plane is being removed. That is, we are cutting this one. So if this is removed, then all the atoms here, corners, and the center, face center, they will not be here, right? Because we are trying to remove this surface. So these atoms are also removed. Now, moving on to that one atom we want to consider, right? So let's say we want to consider this face center atom for easy visualization. Okay. Now, in FCC, the coordination number is 12. That means each atom should be covered, or each atom should bond with 12 atoms. Right? It should be covered with 12. That means the metallic bonds should be 12. I'm not talking about the ionic or covalent bond. I'm talking about metallic bonds. Metallic bonds can be 6, 8, 12. It depends on coordination number. So we are talking about metallic bonds. And please remember, metallic bonds are completely different from ionic and covalent bonds, right? So the nearest neighbors is also called as covalent bond. So there is nothing difference, or even called as the nearest neighbors. So the nearest neighbors are, I will represent them in red color, okay? So one, again it should be covered by 12 atoms. So the nearest neighbor should be 12. Coordination number is 12, so the nearest neighbor also should be 12. So one from here and one another from this guy, right? The lattice next to it. So before that, let me represent three axes, right? So yeah, one plane behind this guy, this is the one plane, and the other plane is before this guy, okay? So there are lattices behind and beyond, right? There are lattices back and front, so that's what it is. There is a lattice here also, and there is a lattice up front also, okay? Now we know. Now coming to this green guy, so this green guy is surrounded by 12 neighbors, and this is 1, this is 2, and the same goes for the down or the lattice next to this one, 3, and the face center of this, the same crystal itself, 4. So we have completed 4, and the other one is this guy on this surface, 5, and the other guy is 6 behind this one, and the same goes for behind 7. Okay, 7, and you have 8, 9, 10, 11. I guess we have missed one. So you have 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So I guess we made a mistake in numbering. So this is 1, this is 2, there is 3. Oh, my bad. We have missed 3. Okay. So let's represent this guy as 3. Right. So I will try to do it more clearly. So this is my guy. Okay. So along let's first atomic plane, okay? The side one, so that you can understand. So this was the FCC that atom we were talking about. So this was the atomic plane we are talking now. This is the one, right? So you have one atom here, another atom here, another atom here, another atom. So the 4 atoms are covered, right? Now, so there goes another atom which will look like, see here, the upper one and the down one. The same here also, the up one and the down one. And the last one will be, let's take green for that. The centers, these planes, this plane, the back plane and the front plane. So they will be looking like. Okay, so they should come forward. So this is how the coordination number 12 happens. It is a bit complex, but if you try to visualize in your own way, then you will understand what I'm talking about. I couldn't find the images very good so that people can understand, because the FCC crystal it has like what 4 effective number of atoms, not 8, not 1 like simple cube. So it is a bit confusing, but anyway. So this is the back plane, this is the front plane, same the back plane, front plane, top plane, bottom plane, top plane, bottom plane. I hope you people can like visualize this thing. See, top, I mean nothing but this one. Right, so that's what I'm talking about. I will just draw a simple structure here so that you people can understand. Okay? So because this will come eventually when you try to do when you find the surface density of atomic planes or the surface energy of atomic planes. This visualization is very important, right? So this is top left, top right. What do you mean top left? This is my top. Let's use green, right? Because I'm talking about green atoms. This is my top left and top right. This is bottom left, bottom right. So this is my bottom left, bottom right. Right? So there is one atom here, that is what we call as top left, and there is bottom left. You have another one, top right, bottom right. So this is about these atoms, the black one, sorry. So the black one, right? Let me change it. Now, moving on to the green one. Okay. Now let me draw the same cube again. There you go. So yeah, we are talking about green now, right? So let's take green because the black atoms are done, right? These black atoms are done, top left, top right. Now we are talking about what? Front. So front plane will look like this, and this is the back plane. See, I will draw this. These are the front one. Okay. Now the back one should look like. Let's take another color. Okay, so this orange. Okay, so the back ones will look like this. The back, and this is the front. Okay, so the front has one atom here. The back will also another atom here. Again, the front will have another atom and the back will have another atom. So back left, back right, front right. I'm connecting these atoms so that you can understand. Okay, so 1, 2, 3, 4, 1, 2, 3, 4, 8, and this is my plane, the simple plane. And this simple plane at the corners has 4 atoms. These guys, yellow. So 4 plus 4 plus 4 will be equals to 12. That's it. I hope I tried my best to make you understand. So these are my top plane, this is my bottom plane. I tried my best, but let's hope you people do understand, okay? So moving on to, now cutting. What is my surface energy? Now, I will not explain again these things, okay? So you people should have this in your back of the mind. I will just draw a structure and I will cut it and I will say this is my coordination atoms. Okay. Please put these things in back of your mind now. So for 100, okay. So this thing will be a constant because it will not change only up to this. The coordination number will change. Okay. So for FCC, this also will remain constant. Z is 12 for every FCC. Okay. So let's take that as K1 constant 1 times number of broken bonds. Now what I'm trying to do is I'm trying to cut along this surface. Cut in half. Right. Now what I'm trying to do is let's again take this atom. So what are the atoms lost? The front one lost, and the front corner also got lost. Right. So we have lost one atom, 2, 3 atom. That's okay. So it's 100, right? Yeah. So how many atoms did I lost? 1, 2, 3, and the atomic plane front one 4. So yeah, we have lost the front ones, right? The front left and front right. We have lost. So this is my front left and this is my front right. And these are simple plane atoms. So 1, 2, 3, 4. So 4. That's it. Now moving on to 1, 1, 0. Let me draw the crystal structure first. I hope you people are able to understand. If you don't, just please go through this one. You have to visualize. Whenever you're trying to cut planes, you have to visualize. Until unless we cannot do anything. This is 100. Now what? Let's take this guy, same. How many atoms are being lost? Okay. Moving on to black. So the front face is gone. Okay. How many did we lost? So the front face. Let's not take this guy because that is far away. So let's consider. Let's do this part also. Let's consider this guy. Okay. We are focusing F on this one. So this guy has lost this one, the front surface one, and this plane. So how many? 1, 2, 3, and then the same, the lattice above. Okay. So the above lattice also he has lost 2 faces, right? Here and here. So how many? 1, 2, 3, 4, 5. K1 times 5. Moving on to last one. 1, 1, 1. See, you people have to visualize. Then only you can just answer it very nicely. So my plane will be this plane. Now the atoms that are being lost. Okay. So let's again take this guy, because it is near to the atomic planes. Okay, so where I have cut the surface. So the atoms that we are trying to focus should lie on the cut surface. If it is backwards or any other thing, then it doesn't make sense, right? We are talking about surface atoms. The same mistake we made. We shouldn't consider here. We should consider on the surface. that atom will tell you the number of atoms are lost. Right? So let's take this guy who has on the arm or the edge. Okay, so this guy has lost 1, 2, the front surface and the top plane, the right front, the top one, and so this guy has lost. So how many atoms he should be covered, right? So front, back one is there. So back atom is there. Top one is gone. Front one is gone, and the bottom one. Okay. No, the bottom one is also there. What? Yeah. Okay. So this is corner one. So the front one, the top one, and the corner one. The number of atoms lost, K1 times 3. Now tell me, among them, who has the lowest surface energy? Lowest surface energy means lowest number of atoms being broken. Right? So the lower the number of atoms that have been broken, the lower will be the surface energy. So among them, the 1, 1, 1 plane has the lowest the atom bonds have been broken. Then I have 1, 0, 0. Then I have 1, 1, 0. So this is how the relation came. This the sir has discussed this relation, but he didn't told you people how we got this relation, right? So this is how we get the relation. Until or unless you assume and have this diagram in the back of your mind, then only you will know how the atoms, the number of atoms that have been broken. Okay? So please just sit somewhere else, quiet, take 2 or 3 papers, take a pen, draw the FCC, and try to coordinate atoms, 12 coordinate atoms from the face. Then you will understand, okay, so if you try to cut from this plane, so these atoms will be gone. That means this many number of atomic bonds will be lost. So then only you will understand, okay, this is how I came. Okay? Now this is about FCC. Moving on to BCC. Right. So what does BCC says? Okay. Now this is my gamma 100 for BCC. So for BCC one is very easy. Right. So let's first tell you the coordination in BCC. Right. So then only you will understand. So let me represent. This is 1, 2, 3, 4, 5, 6, 7. And in middle, you will have another one, 8. So this guy is coordinated with all these ones. So the coordination number is 8. It's simple. There is nothing very complexity there. Okay. So the middle one is bonded with all other 8. And the same, the corner is also bonded with all 8. How? See. Same. The left you will have another crystal lattice. In the back you will have another crystal lattice. So this is 1, this is 2, because here you will have another crystal lattice. And here you will have another crystal lattice. So let me represent those numbers in red so that people can understand them. This guy is 1, this guy is 2, this guy is 3. Now what about the top? On the top also you will have 4. So totally you have 8. So this atom is coordinated with the one center here, the another center guy here, the center behind, same the center here, and the top. So again, these corner atoms also is coordinated with 7 or 8 center atoms. Again, understand, visualize. So the center atom is coordinated by 8 corner atoms, and each corner atom is coordinated by 8 center atoms. Okay. Now let's go on. Let's start with cutting the planes. Okay, this is the most interesting part. Cutting the planes is most interesting part, right? So coming to 100. Let's draw our structure. Let's draw it big so that we can understand. Cube is getting ugly with every diagram. Okay. So yeah, let's take red to cut. Now we are trying to cut here. That's it. Let's take blue atoms. Okay. So yeah, you know what are we trying to focus here? Let's focus with the center atom, because that is the atom which is lying on the cutting plane, right? Because all other atoms are lying behind that guy, right? Actually it is not, but if you zoom on it close, the atom's not sitting like this. So this, if you try to see this edge length will look like this. Okay, this is how the atoms look like actually. This is my edge length, this guy, right? So this is my nucleus. Now, yeah, so this guy is looking, so this guy should be coordinated by 8 atoms, and the back guys are chilling, right? They are not being cut, so he is perfectly coordinated with those. But what about the front guys? The front guys are lost, so that's why you have now K2, it is not K1, because the coordination number there is 12, the Z is 12, now the Z is 8, so that's why I am representing it as K2 times what? The number of bonds being broken are 4. This is easy. Now moving on to 110. Here comes the trick part. K2 times. So this is my plane. This is my plane. Okay. So yeah. So looks like now 110, right? So red, cut the plane. Then now again let's take the corner atom for now, for simplicity. Okay, so these are guys lying here. No, let's not take it. Let's not even take corner atom, because if I take corner atom, then you have to assume the lattices above and below, right? That will be more difficult. So let's write the atoms here. Right. Now when I try to cut here, so everyone is safe here, right? This guy is safe, these are safe. But what about the other two? Right? So this guy is bonded with all these atoms. So here he has 6 bonds. But because we have cut like this, right? So we are cutting in this direction. So this is the atomic cut. Okay? We have removed this part. Right? It should more or less look like this. See how this looks funny. So this is how it should look like. Right? This part. Because we have cut, right? So now these 2 atoms are lost. These 2 atoms are lost. What is the coordination? What is the number of bonds broken with this guy's perspective? 2, right? Because these atoms are safe; they didn't even budge, right? So that's why we have 2. Okay. It's 2. Now moving on to the final one. So atomic name of 111 will be equals to what? 111 will be equals to K2 times. Now we need to know the value, right? Now let me draw the crystal structure. I guess there is some lag between. Okay, so I guess this was a perfect cube so far. So, what is my cutting plane? This. 111, right? So right, so yeah. Now moving on to now let's write the atoms. So where our atoms should be right. So let's take only the ones which are lying on here, right? So for simplicity, let's only take this atom who is on surface. Okay. Now, what are the number of atoms lost? Right. So 1, the guy above this guy. So there is a center atom. The center atom of the above crystal, right? And the same goes for the behind one. Okay. And then you have the below one, right? And there is also the guy here and the guy here. Right. So let me make it more clear. So yeah. So let's first draw the lattices. This is the one. Okay. There is another one. So you have 1 here, you have 2 here, 3 here. And on top again you have, so let's represent it like this. On top you have 4, 5, 6, 7, and this is 8th one. Okay. So on top I have lost this guy. So there is 1 atom coming from here. Okay. So 1 atom from above, from 7th crystal structure. And the same goes for 5, for 3. And here itself we have 4 and the 4th one. So it will be 5. Oh, sorry. Yeah, it will be 6 because there is another atom above this one, right? So everyone is lost besides the bottom one, the bottom this guy, and here the second one and this one. Everyone is lost. So it will be 6. Now tell me, who has the least surface energy? The gamma 110, and then you have gamma 100, and then you have gamma 111. See, you need to visualize, because if you cannot visualize this, you cannot understand. Right? Now, so this is about the surface properties. How our surface affects our characteristics. How our surface affects the characteristics. Right? Now, so what I have, let's not, so let's just only discuss about the surface properties. So again, when we are talking about the octahedron, right? So how this surface energy depends? Now it depends upon cluster, right? The key nanoscale properties will change with respect to the size of the cluster, right? So yeah, and then again the cubo-octahedron we have discussed. So it has both square faces and rectangular faces. So it is also called as a classic Archimedean cubo-octahedron. Okay, it has fixed number of square faces and triangular faces. Okay. Now, again we have discussed the stability. So the nanoparticles will not remain as dispersed. Why? Because of the large number of surface atoms, it is at high energy state when compared to the bulk atoms. So it depends upon size. The smaller the size, the higher the energy of the system. So they will try to agglomerate, and also it depends upon the curvature, right? So see the curvature part. So if you have flat surface, then there will be no. What do you mean? Because the curvature will be depends upon constant upon r, and because r is infinite, the curvature will be 0. So you will have no dependence on this one. Right? The exponential 0 will be 1. So this whole term will become 1, and xv total equals to xv bulk. If there is no what we call concentration gradient of vacancies, then there will be no diffusion of atoms. Right? You need the concentration gradient of vacancies so that the atoms will diffuse, and for that you need different curvatures, the concave and convex. Right? And then we discussed the Wolf construction. Where is the Wolf construction? Yeah, here it is. So here it is, Wolf construction. So what does it define? It defines our equilibrium shape of our particle. Either it is a macroparticle, or it is a nanoparticle, or it is any crystal structure, or it is a cubo-octahedron, or FCC crystal nuclei, or anything. So smaller the energy, surface energy, the better it is. That means the famous relation, which is surface energy times the area, should be minimum. Why? Because the surface energy term is equals to surface energy per unit area. Times area will give you surface energy. So that's why this is, and that should be minimum. Right? So if you have listened to this lecture, you should answer at least 6 questions, because I have covered all the 6 questions here. So I hope people have listened. Now, how the thermodynamics is affecting my, what do you call, so how my thermodynamics affects my structure. Right. So we will not discuss everything. Yeah, and also there is this term, guys, right? The how the so there is the how interfacial energy of a material will change, right? If the size of the nanoparticle decreases, then interfacial energy will increase. So it is an obvious relation, right? There is no need to like ram your heads there. Now coming to thermodynamics part, the most interesting part of nanoparticles, right? Okay, just give me a second. Coming to thermodynamics. So, okay, I will try to derive the Clapeyron equation. Okay, in more detail, right? So that you can understand. So it will be simple. It will not be very difficult. Okay. So we'll just go through it. Now, free energy. So let's start with first law of thermodynamics. Let's not jump into relations. It will again, you will think, oh, what exactly is happening? So it's better to first start with first law of thermodynamics. First law of thermodynamics states the conversion between heat and work, right? So this is my heat and this is my work. And if there is a conversion, then there should be some constant. So there you have the internal energy. That's all. And these are writing in terms of exact differentials, not exact differentials, exact terms. Let's write in terms of differentials. Then it will be del Q will be equals to du plus dw. And why this is exact differential? Because it will finally turn. It doesn't depends upon the path you take. It's a state function. I hope people have studied thermodynamics because these are very simple terms. This is our path function because it depends upon path. What path you take, it doesn't depends upon path. It only depends upon initial and final state. That's all. Right? They also depend on initial and final state, but it also depends upon what path you take. Right? For example, you have to reach from Chennai to Kanpur. You have different paths. You can even come from water to West Bengal. So these del Q and del W depends upon those things, but du depends upon the initial and final state. That's all. Okay, so that's why we call it as a step function. That's it about them. Now, when you came to second law of thermodynamics, you have seen the entropy. So from entropy, you have this free energy. Delta G equals to delta H minus T delta S. This is the exact equation. Let's write in terms of differentials. dG will be equals to dH minus TdS. Sorry. Okay. Now, differentiate by parts. dH equals to TdS minus S. The next one is how do you remove this guy, right? So from second law of thermodynamics, you got entropy. So entropy is state function, and it depends upon del S will be equals to del Q upon T, right? So some part of energy is being lost even at constant temperature. So that's why that relation came. That's it. Now, you know del H is equals to du plus PV, right? The entropy, the enthalpy, the total energy of the system will depends upon internal energy plus the work done. It may be PV or VDP or anything, right? So constant pressure, it should be PdV, right? So dH will be equals to du plus PdV plus V. You substitute this guy. And you substitute this here. So let's take our relations first. I have relation 1, and then I have relation 2, and then I have relation club these things. Then what I have is, what is DH? DH is, let's first write these guys. DU plus BDV plus BDP minus TDS minus STT. What is DU? DU equals to TDS minus BDV. So we have BDV plus BDP plus TDS. This guy goes off. So finally we have free energy in terms of pressure and temperature. So there is also this confusion. Why do we use this guy than this guy? You mostly see this equation whenever you're trying to calculate the free energy of a system or free energy of anything, reaction or whatever it is. You do not consider this guy but this guy. Why? Because the independent terms, the pressure and temperature are easy to measure. Right? Temperature is very easy to measure. You just have to need a thermocouple or a thermometer. Right? And for pressure you just need to have pressure gas. That's all. So that's why we use this equation mostly. Because the terms, the independent terms which define the free energy of a system are pressure and temperature. So if you know the pressure and temperature, you can easily find anything, the free energy of any reaction or any system. So that's why we heavily depend upon this equation. Right. Now, so how these equation affects our system? That is our problem. So for example, I have a nanoparticle in a medium of alpha, and my medium is beta, and a nanoparticle is beta, and where it is present is alpha. Okay. So this is my nanoparticle, this is my medium. Now medium will exert some pressure, that is P1. Right? So for example, if you immerse a balloon in the water will exert pressure throughout the surface of the balloon. Right? Same. Alpha is some medium, so it is exerting some pressure P1, and the atoms inside nanoparticles are exerting pressure P2. Just like the air molecules inside of the balloon. Right? Balloon exerts some pressure on the surface, inside the surface of the balloon. Right? And this change in pressure will result in a surface, a curvature of a surface, which is given by the surface energy times the curvature. Again, I have said before, curvature kappa is given by constant by r. If you are talking about bubble, then it will become 2 by r, this curvature. Right? Please keep this in mind. We are not talking about bubble, right? It's a nanoparticle which has a complex shape. But just like you have seen cubo-octahedron, right? Basic Archimedean, which has n faces, n squares and n triangles. Right? So now we write free energy for each phase. So let's write free energy for each of these phases. dg beta will be equals to, let's write for nanoparticle, v beta dp minus s beta dt. Let's write it for this guy, alpha medium dp dt. Right? Now at equilibrium, when two systems are in equilibrium, then their free energies are equal. The first criteria for any system to be equilibrium with surroundings, the free energy of the system and surrounding should be equal, first of all. And the second point is the value should be minimum. These two needs to be satisfied. So you see most of this, you will not see this guy because you will see only in phase diagrams. That's all. This condition, but not this. Right? This condition was there in there, but still you take this one because the minimum energy defines our system. That's how the Wolf construction also came from. Right? Now that means the G beta will be equals to G alpha. Now if you differentiate on the both sides, it will be G Bg beta, Bg alpha. Simple. Right? Now in order to equate, I will just write it. dP by dt will be equals to what? So delta S by delta V. Right? Now, what is delta V? V beta minus V alpha. Right? Or what should I take? Should I take? Yeah, it shouldn't. Yeah, you have minus term, right? Also this minus term. Okay, okay. Now, so yeah, if you take out minus, then it will be V alpha minus V beta. Okay. Now we know volume of air is very much greater than volume of solids or liquids. Right? We all know that, right? Because the atoms are very far away apart in air when compared to solids and liquids. That's what we have been studying from class what, 4th or 5th standard, right? The density of gas is very less. That means the volume of air is very large when we are comparing to same mole of solid, liquid and things. Right? So that's why our V alpha will be very much greater than V beta. Then V alpha minus V beta is approximately equals to V alpha. Again, what is ideal law? PV equals to nRT or RT. Let's talk about, we are talking about one more. So V will be RT by P because our medium is gas here. The alpha medium is gas. So we have everything with us now. dP by dt is to delta S upon V alpha, and at equilibrium delta H equals to delta H minus delta G equals delta H minus delta H. At equilibrium delta G is equal to 0 because G beta minus G alpha is equals to 0 because they are same. Right? So Gb minus G alpha equals to 0. So sorry, because they are same, then Gb minus G alpha is equals to 0. So that's why delta H by T will be equals to delta S. So we safely change dP by dt will be equals to delta H upon T, and we know our medium is ideal gas, so it will be RT by P. Now substitute that term here. So it is T equilibrium. T equilibrium nothing but T melting. So T equilibrium or T melting. At melting, right? We're talking about melting. Okay. At melting, solid and gas or solid and liquid, both are same. You can take any other thing also. It will not change much. Okay. Or you can just represent a T equilibrium. It will not change much. And then you have so volume, right? So it will be R times T, and then we have pressure. Times pressure. pressure, then dP by dt will be equals to delta H upon R dm times P upon T. So rearranging terms will be delta H upon dm upon dt by t. So long okay. P2 by P1 will be equals to dm d2 by dt. P2 times P1 will be exponential times delta H and then R E right. So P2 times P initial times exponential H this time. Okay, so V beta dP versus beta dt. dP will be V beta minus V and plus beta plus S alpha dt. Yeah, so dP upon dt will be minus delta S upon delta V. And then you have dP T is to delta H heating T melting. dt upon P. Okay, take this one P2 by P1. Just I can take it. Differentiate, integrate. D1, D2, T will be log P2 upon P1 delta H upon dm d2 d1 upon t upon te. Right. So P2 upon P1 is equals to exponential times delta H upon and to T. 1T. This okay. Now this relation will tell us how the difference between this relation will tell you how the temperature dependence or the melting point of solids or nanoparticles, will change with respect to the pressure. This is one relation. And you have another relation that sir has proven is P equals to P initial times exponential. First you have R surface energy scale to RT. Right. This is one relation. And then the melting point relation is given by T equals to TE times 1 minus gamma V beta by R into delta HF. Now this is another relation for melting point. So these are the things related to the thermodynamics part. Yeah. So before we have discussed, so in this session we have discussed Bull diagram is completed, the surface energy part of atomic plane is also completed, and then we have completed the thermodynamics part also. So now, yeah, the last part which we have missed was the atomic density. Right, so how to write the atomic density of any atomic planes. So atomic density planes is given by simple the number of atoms divided by the surface area of the plane. Times the surface energy. That's all it gives. And we have found the surface energy. So it is simple. For example, if I take FCC, right? So let's take FCC. So I have corner atoms, face centers, corner, face center. So here each atom is shared by 2 planes. So and this is shared by 4 planes. The effective number of atoms on what is 110 plane, right? So I have 2 times 4 times half plus 4 times 1 by 4 is 2. So the number of effective atoms on 110 plane is 3 divided by the surface area of the plane. How do you find the surface area? So this is my atomic length, lattice parameter same as h, and this is my diagonal, which is root 2a. So my area will be root 2a square times my surface energy part, which is k1 times the number of bonds being broken will be for 100 is 5. So 15 upon root 2a square times k1, and there is also your coordination number which is 12. So 3 5s, 3 4s, 5 by root 2 4 a square, 4 root 2 a square times delta hf by L naught. So this is how you find the surface density of 100 atomic plane. Let me draw it for 111 plane because this is the most complex one. Right, so this is how it looks like. Okay. Now each corner is shared by 6. Why? Because the angle here is 30. each atom at the corner of 111 plane is being shared by, so let me draw it again. Yeah. So each atom at the corner of 111 plane is shared by 6 planes. Why? Because the angle, it is an equilateral triangle. Yeah. So the angle here is 60. I said before 30, right? It's not 30, it is 60. It is an equilateral triangle. So 360 upon 60, it will give you 6. So each atom is shared by 6 planes. And what about at the edge? It is shared by 2 planes. Right? So the other plane will look like this. So I have 3 on the corners. 3 times 1 by 6 plus 3 times 1 by 2. Right? So 3 by 2 plus 1, which is 2. So the effective number of atoms on 111 plane is 2. And then we have to find the area. So root 2a so this is root 2a, this is also root 2a. Right? So root 2 should be 2s squared. Now, effective number of atoms, which is k1 upon a square. That's all. So that's all for today's session.